You type a prompt for a sleek, futuristic sports car on a coastal highway. For the first second, the output matches the request. Then the car morphs into a horse carriage and finally melts into a spaceship. To control this, creators rely on rigid text prompt structures. The formula dictates specifying a subject, an action, a scene, and a camera movement to give the AI exact parameters. Even with strict parameters, the visual details drift. Within a few frames, a character's shirt changes color. Objects in the background shrink or completely hallucinate into different shapes. Current text-to-video generators hit a quantitative limit quickly. They can only output 2 to 6 seconds of accurate, contiguous footage. Structural prompting fails to solve the drift because the neural network is generating frame-by-frame visual correlations. It has no underlying world model to track an object's existence through three-dimensional space over time. To bypass this hallucination problem, technical creators use a workflow called hybrid keyframing. The process requires generating a static identity anchor. This single image serves as a strict, non-negotiable master reference for a character's appearance. Creators then run an image-to-video model through a shot factory loop. They force the model to animate surgically constrained 2 to 4 second sequences based entirely on that locked anchor image. This requires massive production overhead. Creators write one-page continuity Bibles, manually verify lighting and props, and wardrobe for every single clip. Hybrid keyframing is a manual, brute force patch. It requires intense human labor to compensate for the AI's architectural inability to maintain temporal memory. To understand why this temporal drift happens, we have to look at the mathematics of diffusion models. This animated scatterplot graph visualizes a high-dimensional space. Here, the intensity values of individual pixels act as coordinates. Real, coherent images cluster together on this structured mathematical manifold, shown here as a tightly packed spiral of dots. In this system, adding noise to an image is mathematically identical to a random walk. The data points diffuse randomly outward from the structured manifold, expanding into an unstructured cloud of pure noise. To reverse this Brownian motion, the neural network learns a score function. This is a time-varying vector field, represented by this grid of arrows, which points generally back toward the original structured spiral. As the time variable approaches 0 during generation, this vector field refines. The arrows guide the random noise points step by step, coalescing them perfectly back onto the distinct two-dimensional spiral shape. The score function maps random noise to a realistic image flawlessly, but it calculates this process in an isolated mathematical vacuum, completely devoid of temporal context or continuity from the previous frame. Text prompts influence this geometry using an embedded vector space. Models use an embedding space, like CLIP, where the mathematical representations of text descriptions and their corresponding images are aligned. During generation, the model predicts the required noise removal twice simultaneously, once governed by the text prompt and once completely without it. We see these independent predictions here. For a single point of noise, the gray arrow points toward the general average of the training data. The yellow arrow points toward the specific target class requested by the prompt. The system subtracts the unconditioned gray prediction from the conditioned yellow prediction. This isolates the exact mathematical direction of the text prompt. This resulting direction is then multiplied by an alpha scaling factor. The vector increases in length, aggressively shoving the noise point directly into the desired class region of the manifold. This specific mathematical vector manipulation is called classifier-free guidance. Classifier-free guidance recalculates this massive vector shift from scratch for every generated frame. Because it does not reference a continuous state, it mathematically guarantees morphing and hallucination over time. Eliminating temporal drift requires abandoning stochastic frame-by-frame generation. The solution lies in architectural engineering. The Loci-Looped model is an architectural design that natively learns intuitive physics. A single input frame passes through an encoder, splitting into parallel isolated pathways labeled slot 1, 2, and 3. Each slot captures a distinct object. Inside, the stream bifurcates, Gestalt codes for shape and positional codes for coordinates and size. The Gestalt codes pass through an information bottleneck, where they are binarized. This forces the network to factorize the actual entity, rather than merely memorizing local pixel arrangements. Dedicating isolated neural architecture to individual objects establishes the prerequisite for object permanence. The network tracks an entity independently of its surrounding environment. This slotted architecture is tested when an object is visually occluded. When visible, a pixel observation node feeds the slot state through an open percept gate. If obscured, the feed goes dark and the gate shuts. Immediately, an inner latent imagination loop illuminates, feeding predictive updates based entirely on the object's trajectory. This dynamic, autonomous switching between pixel observation and latent imagination is the mechanization of intuitive physics and directional inertia. To stress test this architecture, researchers ran Loci-Looped through the Adept dataset vanish scenario, tracking objects as they move behind extended physical occlusions. This bar chart compares the tracking error metrics across different architectures. Older models like Savvy and G-SWAM show massive error bars exceeding 26 pixels. Loci-Looped displays a tracking error of just 2.6 pixels. A 2.6 pixel tracking error means the model successfully and autonomously anticipates the exact frame and location of an object's reappearance from behind a screen. The future of AI video generation relies on latent world models capable of genuine autonomous physical reasoning, not manual keyframing or refined text prompts.